Modern living rooms are noisy. High-definition televisions stream movies, gaming consoles ping the network, and smart displays glow, constantly competing for attention. But 5 times a day, the Islamic prayer, or Adhan, requires complete environmental focus and exact, predictable timing. When that exact minute arrives, your digital environment doesn't care. The TV keeps blaring, forcing a sudden scramble to hunt down remotes and silence the room. You might think a simple smart home routine could pause everything, but these devices operate in heavily guarded, closed ecosystems. An Android TV and a Google Nest Hub actively resist communicating natively. Without an invisible orchestration layer forcing them into sync, your entertainment hardware will continually collide with your daily rituals. Getting hardware to cooperate over a local network is a notoriously fragile process. Standard casting protocols suffer from unpredictable lag, meaning a scheduled audio track rarely plays exactly when you need it to. Engineers call this the network zombie problem. A powered-off smart TV's network interface often stays awake, pinging the router. Believing the TV is awake, basic automation scripts send pause commands that just bounce off the standby screen and time out. To bypass these dead ends, the entire living room needs a single localized master clock, one that executes commands with deterministic, millisecond-level precision. That master clock lives right here, on a $35 Raspberry Pi 4, running a custom Node.js orchestration server. It manages 10 distinct microservices that handle timing calculation, device life cycles, and media states. For a specialized IoT engineer, mapping out this hardware logic takes roughly 3 weeks of dedicated work. But this specific architecture was rapidly prototyped, tested, and deployed in just a 4-day sprint, entirely through an AI-native pair programming workflow. This chart illustrates the acceleration gap. We are looking at a drop from an 80-hour manual baseline down to just 10 hours of AI-assisted development, all while generating 182 precise code commits. When the friction of looking up low-level hardware syntax is removed, the engineering focus shifts from the minutia of line-by-line debugging to the higher-level design of the system's logic. Let's look at how this plays out in real time. 5 minutes before a scheduled Adhan, the system initiates a pre-flight sequence. Instead of building visuals on the fly, a rendering engine uses FFmpeg, a powerful media processing tool, to stitch together high-definition atmospheric effects based on the current local weather, holding the payload in a ready state. Then comes T0, the exact millisecond the scheduled prayer time strikes the master clock. This flow diagram outlines what happens next. The system uses the Android Debug Bridge, a command line tool for device communication, to run a deep state inspection on the Sony TV, find the active media stream, and instantly fire a pause override. Simultaneously, the pre-rendered weather dashboard and the high-fidelity Adhan audio are cast directly to the Google Nest Hub Max. By staging the heavy visual processing early and using direct network protocol injections instead of standard APIs, network lag is practically eliminated. The environment reacts perfectly. To verify this timing day after day, the system monitors its own health. A live operations dashboard tracks hardware states, counts active microservices, and maintains a 99.9% success rate. Keeping a local server running indefinitely is incredibly difficult. Long-running network listeners naturally consume more and more memory over time until they exhaust the device and crash. To prevent this, standard timers were completely stripped out. The architecture relies instead on serialized recursive promises, a coding pattern that forces one network request to fully complete and clean up before the next one starts. In production IoT, getting a script to run once is just a prototype. Real-world reliability depends on a self-healing infrastructure that sustains itself for months without human intervention. 3 to 4 minutes later, the audio track finishes, signaling the end of the automated event cycle. The teardown phase begins. The connection to the Nest Hub elegantly terminates, clearing the visual dashboard and returning the smart display to its resting state with 0 human input. Down the hall, the Android Debug Bridge sends one final silent command, telling the TV to resume your Netflix movie or YouTube video exactly where it left off. Rapidly solving these hardware interoperability conflicts with AI creates the engineering headroom needed to refine every transition. This results in a system that accommodates daily tradition with a surgical precision that respects the sanctuary of the home.